So if I go down, the last thing we did was we looked at the mechanism for the nitration of benzene. So if you remember, benzene can't react with nitric acid very well, so it needs some help. So the catalyst used is concentrated sulfuric acid, and there's a temperature requirement of 50 degrees C. Remember, if you go higher than 50 degrees C, it will lead to polynitration, so multiple substitutions of nitro groups, and you can form potentially explosive substances. So that's not a good idea. So the way that they do it is they use they react the two acids together to form the electrophile, which is the nitronium ion NO2+, and then that interacts with the benzene ring. It's actually the pi electron cloud where the interactions between. So you get this interaction here. So a pair of electrons from the cloud comes out and forms a covalent bond with the nitrogen with one of these carbons. It sets up the intermediate, which is unstable. Remember that hydrogen was always there, we're just short in this part of the mechanism. Remember to try and cover 5 carbons with your partial electron cloud, positive charge in the middle, and then to stabilize itself it loses this pair of electrons here. So take a curly arrow from the middle of the CH bond and it goes back in to reform the pi electron cloud. This H comes off as an H plus ion, which then reacts with the HSO4 minus ion that was formed in the first step, and you reform your catalyst H2SO4. So that's the mechanism there. Okay, so we're just going to continue. You're going to see some repetition with some of the other reactions. So it gets quite easy now. As soon as you've got your head around this, it gets very, very easy because all the mechanisms are pretty much the same. Okay, so the first of tonight's reactions involves the halogenation of benzene. So that's obviously the reaction with between benzene and a halogen. So we're going to use bromination to explain this one. Okay, so benzene is unable to react with halogens unless a catalyst is present. This is due to the low electron density of the delocalized ring of pi electrons, DROPE for short. A friend of mine works at Newcastle Uni and he uses that acronym. But whatever you do, don't put DROPE in the exam, okay? It's just a way for you to remember the sort of key words, delocalized ring of pi electrons. So that delocalized ring of pi electrons with its low electron density is unable to polarize the halogen molecule, and so the reaction needs a catalyst, and the reactions are referred to as halogen carriers. I'll explain that when we get into the mechanism. Okay, so bromination of benzene at room temperature and pressure and the presence of a halogen carrier catalyst, benzene will react with bromine to form bromobenzene. Suitable catalysts are FeBr3, iron 3 bromide, or AlBr3. And you'll notice there in brackets it says iron and aluminium can be used, so the metals themselves can be used because they actually form those catalysts in the reaction. So what would happen is the iron and the bromine would form iron bromide, FeBr3, and then the reaction can take place. Okay, but it's easier to just add the catalyst as FeBr3 or AlBr3. Right, okay, let's go to the overall reaction then. So benzene plus bromine, Br2, and I'm going to just show the catalyst above the arrow. Let's go for FeBr3, but I could use AlBr3 instead. Okay, and what we're going to get is a mono substitution, so that's a single substitution. Just put it in the 12 o'clock position. But I could put the bromine on any carbon because they're all equivalent, and we get HBr. Okay, so straightforward substitution reaction. Okay, so the mechanism, so we'll break it down into the steps. So hopefully you'll see some similarities with the nitration mechanism. So the first thing we've got to do is form the electrophile. So just without this, imagine if that wasn't there, these two don't really interact with each other very well. and we said that this is a low electron density because all these electrons are kind of spread out amongst all 6 carbons. So a low electron density is unable to polarize this non-polar bromine molecule. This is year 13. So here we go. So Br2 plus the catalyst, so FeBr3, and that creates the FeBr4 minus ion and a Br plus ion. I'll just circle that because that's the whole point of that reaction, is to create that Br plus ion. That is your electrophile. Okay. Now, if you look in other textbooks, you might see a slightly different version of that reaction. This is the one I always use, and it's absolutely fine. It's one of the ones mentioned or requested by the exam board, so I'm happy to just stick with that. I'm not going to confuse things and show you different versions. Okay, right, so now we take the benzene ring, we bring the electrophile into play. Okay, same as before, pair of electrons from the delocalized ring of pi electrons. Okay, so remember, take your curly arrow from the circle, this circle here. Don't take it from the hexagon. And then what we'll do is we're going to create an unstable intermediate. So I'm just going to play around with the position of the substitution just to show you the different ways you can draw. Let's put it here. Okay, so that's the hydrogen that was already there. That hydrogen is there. We're just not showing it here, but we are here because we need it for this part of the mechanism. There's the bromine on now. Okay, so this pair of electrons is this pair of electrons here. Now, because I've put it at this sort of 6 o'clock position on the ring, my partial electron cloud, I'm going to draw like that. So you can see I'm still covering I'm covering 5 carbons with that. Okay, it's open where the substitution's happening, and I must put that plus sign in. Okay, just to show you different ways you can draw these things. So just as before, that's unstable. So how does it stabilize itself? Pair of electrons from the carbon-hydrogen bond go back into the ring, and it generates the 6 pi electrons back. There's your bromine on, and there's that H now as an H plus. Okay. Would you lose marks if I always tell my students to take it from the actual edge of the circle. I would need to check on that one. So I know what you mean. You're talking about sort of if you did that. I would take it from the edge of the circle personally. Okay. Not an examiner. Maybe when I retire, I might think about marking exams, but not at the moment. So I wouldn't like to say. Okay. And then all we've got to do now is reform the catalyst. So I'm sure you can predict the reaction. So that H plus ion that we've just formed and the FeBr4 minus ion, which was generated there, they react together and form HBr, and there's the catalyst back, FeBr3. Okay, so that's that one. Nice and sort of familiar, I would say, to the previous one, hopefully. Okay, so if you're happy, let's just crack on. All right then, so alkylation now. I'll just move the page up, sorry. Alkylation. So we've had nitration. That was the reaction to put a nitro and NO2 group onto the benzene ring. We've just seen halogenation, and I used bromine as the example. I could have gone for chlorine. And now I'm going to do alkylation. So this time I'm putting an alkyl group onto the benzene ring. So I'll just read through the sort of introduction. So in alkylation reactions involving benzene, a hydrogen atom on the benzene ring is substituted by an alkyl group. So what's an alkyl group? It's basically something like a methyl group or an ethyl group. It's just an alkane with a hydrogen missing. A haloalkane provides the alkyl group, and the reaction is carried out in the presence of an AlCl3 catalyst. And the reaction is sometimes referred to as Friedel-Crafts alkylation because of the names of the two chemists who came up with this process. Okay, so they got their name put to the reaction. And then the next little paragraph or sentence, alkylation reactions are important reactions in organic synthesis as they increase the length of the carbon chain by forming carbon-carbon bonds. Now if you're doing OCR, I know some of you are doing different exam boards to OCR, but if you do OCR, part of the year 13 organic chemistry is all about carbon-carbon bond synthesis. So you will see this again, okay? You would see this again when you actually cover that topic. So this won't be the first time, say, my students would see these reactions, okay? So example I'm going to use is the formation of methyl benzene, okay? So methyl benzene is benzene ring with CH3 attached, okay? And just beware this connectivity. I was at a meeting actually, just as a quick aside, a meeting yesterday with OCR, the exam board, and they're really hot on this connectivity. So if you don't connect the correct atoms together, you will be penalised, okay? And that came from OCR. All right then, so the reaction, benzene ring. So if we wanted to put a methyl group on, what have we set up here? A haloalkane provides the alkyl group. So we need an haloalkane that has this methyl group in. So what are we going to use? We'll use chloromethane. Okay, because you can see that's got that CH3 group in it. So whatever alkyl group you want to put on to the benzene ring, you just take the haloalkane that has that group in it. Okay, so let's just put the catalyst across the top there. So that's, we're using AlCl3 for this one. Okay, that's the catalyst. And let's just finish the reaction off. CH3, and we're going to get HCl. Okay. So straightforward. Hopefully you agree that's nice and straightforward. So the next one, going quickly on, I'll keep an eye on the chat and just see if there's any questions, but doesn't seem to be at the moment, apart from the smallest benzene ring that you've seen, which is great. Right, acylation now, okay? So acylation reactions involving benzene. A hydrogen atom on the benzene ring is substituted by what's called an acyl group, for example, CH3CO. So I'll tell you what I'll do, I'll just show you what that looks like. So CH3CO is CH3 C double bond O. Okay, so obviously there's room for another bond there, because obviously carbon can form 4 bonds. It's only forming, if I put that bond in there, it's only forming at the moment 1, 2, 3. Yep, so there's room for another bond there. That's right, Jack. Yeah, carbon-carbon bond synthesis also includes the nitriles and hydroxynitriles. Yep, spot on. So that comes into play when you look at reactions of carbonyls. Yep. Okay. Could you use FeCl3 here? It tends to just be AlCl3. So you get the option for FeCl3 or AlCl3 if you were reacting benzene with chlorine. But if you were wanting to put an alkyl group on, the preferred catalyst is the AlCl3. Okay. Right, so where was I up to? Yeah, I've just circled the ethanoyl group. Okay, so that leads to the formation of an aromatic ketone. I'll show you all this in the example. An acyl group, an acyl chloride, sorry, provides the acyl group. So the acyl chloride here would be just a chlorine on there. Okay, so you're seeing some organic compounds that you maybe haven't seen before here. But anyway, that would be the acyl chloride that you would use to get that acyl group from. Okay, so it's really straightforward. Whatever the acyl group is that you want, you just put a chlorine on the carbon with the double bonded O on as well. Okay, and again, we've got this aluminium chloride catalyst. And the reaction, because it's using that catalyst, it's sometimes known as a Friedel-Crafts acylation for the same reason as before, because the guys who came up with this were called Friedels and Crafts. Okay, Friedel and Crafts. Right, and again, acylation reactions are also important because they increase the length of the carbon chain by forming CC bonds, just like we had there. I didn't point out the CC bond, but there it is. Okay. Right, so the formation of phenylethanone. So if you remember, that came up as one of the named aromatic compounds last lesson. So phenylethanone is the benzene ring takes the phenyl name because we've got a functional group in the substituent. So ethanone only has 2 carbons, and there was some sort of discussion or dispute as to whether this was a ketone or not, and I can hopefully convince you that it is. So just a reminder, okay, a ketone has a carbon, then the carbonyl group, then a carbon, okay? An aldehyde has a hydrogen on the C double bond O, okay? So this is definitely not an aldehyde, so it's a ketone. So this is a phenyl group, phenyl ethanone. I know it seems a bit weird because you've only got 2 carbons in this part, but because that is a carbon, it is a ketone, all right? Okay, so how would we make that? You would take benzene and you'd react it with, so remember, to get this group on here, we're going to use the appropriate acyl chloride, so CH3COCl, okay, so that's ethanoyl chloride. You can see I've got the displayed formula of that here as well, if you wanted to see another way of drawing it, okay, and just move that up in case my thumbnail's in the way. Put the catalyst on your arrow just so you don't forget it's there. C double bond O, CH3, and obviously you're going to get HCl as well. Okay, so that, believe it or not, they are all the reactions that you would need to know about. Okay, so obviously, you know, there are more complicated versions of these with sort of more complicated acyl groups on or alkyl groups on, but the sort of process is very, very straightforward in my opinion. I think once you've got your head around this, you can't really go wrong. Okay. Right, so this is the last part of the benzene bit of the topic, and then it moves into phenol. And so therefore, there's like it's a nice little way to sort of revise things that is the suffix oil. Is oil the suffix for acyl chlorides? Yeah, so ethanoyl chloride, propanoyl chloride, yeah. So this little bit of the syllabus here is a very, very commonly asked question or frequently asked question where you compare the reactivities of benzene and cyclohexane, and there's also a similar thing we'll do at the end of the phenols bit of the aromatics as well. Okay, so we'll do this one first, obviously, because it's part of the benzene stuff. So benzene and cyclohexane both react with halogens such as bromine, but do so in different ways and with different reactivities. So the question when it's asked is kind of getting students to explain what are the differences in the reactions and why do you have those differences. Okay, and I use this a little page to illustrate that. So the first thing we'll do is just remind ourselves of the two reactions. So benzene and bromine, saw that about 10 minutes ago. Benzene plus bromine, AlBr3 or FeBr3 you could use, AlBr3, okay, so that's your catalyst, is going to form bromobenzene and HBr. And the mechanism type is electrophilic substitution. Okay, and then if we move on to cyclohexane and bromine, I don't think I've done any alkene chemistry with you guys. I think I'd sort of done all of that before I started these live streams. But anyway, here it is. So cyclohexane, there's your cyclohexane plus bromine, and that doesn't need a catalyst. So we'll not put anything across the arrow. And what we're going to get, we're just going to get the two bromines adding across the double bond there. Okay, so this is an example of, it's still electrophilic, but now it's addition. So straight away you can see some differences. So let's just point out the differences. We've got a catalyst needed for this reaction and its substitution. No catalyst needed for this reaction, and we've got addition. Okay, the common thing is they're both electrophilic. All right, so let's look at the reason for the difference in the reactivity. Okay, so what I'm saying there is the reason for the difference in the reactivity is due to the nature of the pi electrons. So that's what I'm going to highlight. That's what it's all about. So what have we got going on in benzene? So what can we say about the pi electrons? So the pi electrons, I'll answer that in a second, okay, about the different papers. Pi electrons are delocalized. What examiners want to see is the proper terminology being used, okay? So the pi electrons are delocalized in benzene, okay? So if you want a little reminder of what does delocalized mean, electrons are being shared between more than, that's the definition, more than two atoms, two carbon atoms in this case. So in benzene, the pi electrons are actually shared between all 6 of the carbon atoms, aren't they? Okay, so they are delocalized, they're shared between more than 2 carbon atoms. You're welcome, James. Good name, by the way, same as mine. So that's that one. So let's do the same for cyclohexane. The pi electrons in cyclohexane are localized. Ooh, Jack, it's not it's not substitution at all, it's addition, I'm afraid. Okay, so sorry to sort of cut you down on that one, but yeah, benzene has been monosubstituted, you're right, but cyclohexane has not undergone substitution, it's undergone addition. Pi electrons, getting back to this, cyclohexane, pi electrons are localized. Okay, so there's a nice key term there. May as well define localized. It's where electrons are shared between 2 atoms. Shared between 2 carbon atoms. Okay, so we've got a difference straight away in the way the pi electrons are organized. So what we're going to say is for benzene, because the pi electrons are delocalized, that means the electron density Yeah, I've got to read it. You'll cringe at this, mind. But my way of telling my students that it's addition is when it's a Spice Girls song. God, how corny is this? I won't sing it. Two become one. That's a way of remembering. And all addition reactions involve two reactants becoming one product, as sung by the Spice Girls. It's very kind of them to give us chemists to help, isn't it, in our studies. Right, so back to this. Electron density of the pi electrons is low, okay? So because they're spread out, because the pi electrons are spread out over all 6 carbon atoms in the benzene ring, we say that their electron density, 2 become 1, Laura, surely you know that. Are you too young? Oh dear me, I'm feeling really old now. Electron density of the pi electrons is low, okay? Whereas in cyclohexane, the pi electrons are basically concentrated here, okay, between these 2 carbon atoms, and so their electron density is high. So electron density, sorry, my writing's getting really bad, I'm trying to write quickly, of the pi electrons is high, okay? So moving on from that then, so if benzene has got a low pi electron density, that means it is unable to polarize. Now we're talking about bromination, so it's unable to polarize the Br2 molecule. Okay, whereas cyclohexane, because it's got a high electron density for the pi electrons, it can polarize the bromine molecule. Hope this is all making sense, by the way. And the final thing we'll say is because benzene can't polarize the bromine molecule, bromine is not attracted to benzene. Okay, so without the catalyst, they won't react. All right, whereas there's no need for a catalyst for cyclohexane because the bromine, the Br2 molecule, because it becomes polarized, is attracted to benzene. Okay, absolutely bang on, 7:30, sort of 10 seconds over. So I think that's pretty good going. I know I've gone very, very quickly. Could I explain what I mean by polarization? Of course. So if I just use under the table here, okay, so if I look at cyclohexane first of all, okay, so if we've got a bromine molecule, now this is a non-polar molecule, yeah, because, I'll tell you what, if I move it over there, okay, so bromine is a non-polar molecule because they have identical electronegativities, the 2 bromine atoms. So the electron pair in the covalent bond is sitting straight bang in the middle of that bond, okay? So there's no permanent dipole across the bond, okay? Move it closer to the double bond, okay? And what will happen is the electron density here will repel the electron pair in that bond closer to this bromine here because they're negatively charged. Obviously these electrons are all negatively charged, so there's a repulsion, and that pushes the electron density. So if I just put a little arrow there, the electrons are being moved towards the right hand side of the bromine molecule, which makes that end of the molecule slightly more negative than the left hand side, so that's slightly positive. in relation to the right hand side. So because of that, we now get an attraction from the pi electrons to the slightly positive bromine, and then that bond will break by petrolytic fission. Okay, hopefully that answers your question. Bromine and benzene, they would just sit there quite happily and nothing happens because that pi electron density is too low to polarize this bond. Yeah, I'm sorry, I could see your question, James. 6, yeah, definitely 6 marks for something like this, definitely. Okay, and it's quite a common question. They'll either do this or they'll do the phenol with benzene comparison. Okay. Hopefully that made sense, Alice. I think the fact you said perfect, I think maybe hopefully it did. Okay. Right. Phenol, phenols and phenol. How are we doing for pages? How many pages have I got? 1, 2, 3, 4, and then the last page is just a table, which we don't need to worry about. I would love to get this finished tonight, so that's why I'm kind of moving through it fairly quickly. Hopefully not too quickly for you. Right, phenols and phenol. Okay, so phenols are a class of aromatic compound. So they've obviously got they've got a benzene ring. Okay, but they contain a hydroxyl, not hydroxide, hydroxyl, not hydroxide. Oh yeah, sorry you asked that before, didn't you? Yeah, 3 papers. Paper 1 is physical chemistry and transition elements, I think it's called. Paper 2 is the organic paper, and then paper 3 is called is it unified chemistry, I think, and it basically could be anything. Okay. Papers 1 and 2 have multiple choice, 15 multiple choice questions at the start, and then the rest of the paper is sort of normal questions. The paper 3 doesn't have any multiple choice. Okay. Right, I've got something to tell you about something I've made today. I'll show you it if you want. If some of you want to hang on at 8 o'clock, I'll just quickly show you. And I wouldn't mind some feedback actually, because I haven't told anybody about it yet. So you'll be the first to see it actually. Right, phenols and phenol. So aromatic compounds, they've got a hydroxyl group, but it must be directly bonded to the benzene ring. Okay. The simplest member of the phenols is actually phenol itself, which has the formula C6H5OH. So we'll draw that in the table. Phenol is literally just a benzene ring, okay? But instead of a hydrogen, let's say here, we've got an OH group. So that's phenol, C6H5OH, okay? Just beware this connectivity. So many times, I'm afraid, if there are any of my students in the room, I'm really sorry, I'm not going to name and shame anybody, but so many times students will do that in an exam and I can't give you marks for that, because obviously the hydrogen is not bonded to the carbon, the oxygen is, so I need to get rid of that and put that back. Okay, right, next one, 4-hydroxy benzoic acid. So you can see from the name, I'm sure, that benzoic acid or the carboxylic acid group must be the most important or highest priority. So let's put that up the top there. And basically we just want the hydroxy group to be 4 carbons away from here. So that's 1, 2, 3, 4. So OH directly opposite. I'm just going to rub that out, it's a bit messy, sorry. It's a very common mistake, Laura. That's why we mention it, because you know it's so easy for students to make. You know, I don't want to sound too annoying, but careless mistakes. You know, sloppiness costs marks, and it's so easily avoidable as well. Right, next one, 3-nitrophenol. So notice this is called phenol. So let's put the OH in. That's obviously carbon number 1. 3-nitro means that the nitro group is 3 carbons away. Let's go around this side for a change. So 1, 2, 3. So we're going to put it here. Just careful with your connectivity. Remember, it's the N bonded to the carbon, so you would write it like that. Okay? I'm hoping you can see that okay. I'll just move it more into there so you can see that. Tidy that up a bit. So James, I've been doing 7 p.m. on a Wednesday and it's 3 p.m. on a Friday. Okay, 3 o'clock on a Friday afternoon. No, thanks. Right, and the final one, 1-phenyl ethanol. Okay, 1-phenyl ethanol. So let's just think about this. We've got ethanol is CH3 CH2OH. Yeah. Phenyl is obviously a benzene ring without a hydrogen on it. Now I'm just going to do some numbering here. So this carbon here, the carbon that's got the OH group on, is actually carbon number 1 in ethanol. Okay, so if we're going to make 1-phenyl ethanol, we need to do this. So there's the phenyl group, it's obviously a benzene ring, but we need it to join to, so it's that. So it would look like that. Okay, or if you wanted it sort of fully displayed, you could do it like this if you prefer. Okay, I like to throw that one into my students just to get a bit of practice at naming. Okay, so remember that's carbon. The carbon with the functional group 1 is carbon number 1. No, Jack, you don't need to know the priorities of the different functional groups. No, no. In a way, I know it's probably not what you want your teacher to say. I know I'm not your teacher, but it would make our jobs easier if we had to teach the priority groups, the priority system, because it would help with naming things. I always mention it, but then I do notice students start to panic and think, do I need to know this? Even though I'm saying to them, you don't need to know this anyway. So you don't need to know the priority groups. Okay, so I hope that's okay for naming phenols. So you can see, oh, the thing I've forgotten to say here, and the other reason I use this is actually not a phenol. Hopefully you can see why. It's not a phenol. The CH2OH is the first carbon because it has the functional group on it. It's got the OH group on it. Yeah, I'll draw it a different way for you if you want. Just do it like this. So we've got CH3 CHOH. You could draw it like that. Okay. Now I need to move off this soon because it's eating up a bit of time here, but what's happened is you've got 2 hydrogens on this carbon, haven't you? So you've got a bond going to that carbon, a bond going to the O of the OH group, and then 2 hydrogens. All we've done is taken one of these hydrogens off and swapped it for a phenyl group. That's all the molecule is. Okay? But this is not a phenol because that OH group is not directly attached to the benzene ring. Okay? Whereas in all of these, it is. Right, I'm moving off, sorry. Okay, acidic nature of phenol. Phenol is slightly soluble in water, and when it dissolves in water ever so slightly, it partially dissociates. Okay, so basically it sort of splits up into its ions, its constituent ions. So what happens is, I'll put the OH group here, okay, you get a reversible reaction and you get this ion here, Okay, and you get the H from the OH group dissociates off as an H plus ion. So that is why phenol is acidic, because it dissociates or donates an H plus ion. Remember, proton donors are acids. This is donating a proton. Okay. Reversible arrows show that it's weak, it's partially dissociated. That's what those reversible arrows signify, so it's a weak acid. Okay, very weak acid. And we'll just name this new ion. This is called the phenoxide ion. Okay, mightn't have seen that before. Right, okay, so hopefully this is not going to mess with your heads too much. Right, compared to other organic compounds, okay, phenol is more acidic than ethanol, but less acidic than carboxylic acids. So look at the order of these reactions, or look at these, sort of what's going on in these reactions. Ethanol does not react with strong bases such as sodium hydroxide, or with weak bases such as sodium carbonate. Okay, so that's telling you that ethanol is not acidic. Okay, it won't react with strong bases, it won't react with weak bases. Phenol is very weakly acidic, so what it will do is it will react with strong bases, but it can't react with weak bases such as sodium carbonate. Carboxylic acids react with strong bases such as sodium hydroxide, and it can react with weak bases such as sodium carbonate. So I often, at that point in my lesson, I would then say to my students, how could you distinguish between these three? Okay. So I don't know whether the delay might cause this to be a bit of a pain, actually. I was going to throw that out as a question if anybody could work it out, or shall I just tell you? I think I'll just tell you. Right, so how could you distinguish between these three? Okay, so phenol and carboxylic acids are both acidic, okay? So they would cause indicator paper. It's very simple, by the way, this answer. You could use indicator to determine which one was the ethanol, and it wouldn't turn the paper. Jack, you see, the thing is, we need to know, go into the acids and bases topic. They're both classed as weak acids, but carboxylic acids, this is going to sound really strange, but carboxylic acids are stronger weak acids than phenol, okay? So you could rule ethanol out straight away because it wouldn't give you any kind of, it wouldn't register with something like a universal indicator paper. So you wouldn't get the classic colour produced in your universal indicator paper. So your ethanol's gone straight away, okay? So you'd say you're left with phenol and carboxylic acid. So if you notice, phenol and carboxylic acids both react with strong bases, but phenol does not react with sodium carbonate. So all you would do is put sodium carbonate in both. The phenol can't react with it because it's too weak, so that wouldn't do anything. So you would not see the characteristic bubbles of carbon dioxide. However, the carboxylic acid would, and you'd get bubbles. Yeah, okay, people are saying that now, so that's it. So it's fairly straightforward, isn't it? Hopefully. Right, reactions of phenol. So there's not many of these. I think there's, what is the 3, I think, altogether? Yeah. Right, so first reaction is with sodium hydroxide we'll look at. So I've got 2 representations of this for you. Phenol reacts with sodium hydroxide to form a salt and water. It's a classic neutralization reaction. So phenol plus, oops, forgot the OH group, plus NaOH makes, so what we're going to do, it's a salt, remember, so definition of a salt, the H plus ion of an acid is replaced by a metal ion, so that's what we need to do. So we're going to do this. O, and in lots of textbooks the charges are shown, so we could represent it like that, or you can represent it like that, but you must never put a bond between the O and the Na, because that there is a covalent bond, so you can't do that. Okay, let's put the charges back on. Okay, and we'll get H2O. Keep doing this, don't I, with my that corner of the benzene ring is causing me a problem tonight. I don't know why. So what's this called? It's called sodium phenoxide. Okay, and another way to draw that, to write that equation, is literally just C6H5OH, that's your phenol, plus NaOH goes to C6H5ONa. You put the charges in if you want, okay, and H2O. So that's that one. Next one with bromine, so let's look at what it says. Phenol reacts with aqueous bromine in an electrophilic substitution reaction to form a white precipitate of 2,4,6-tribromophenol and hydrogen bromide. We're going to talk about this reaction again on the next page. So let's just put this into an equation. So phenol reacts with bromine. I'm going to balance this in a second, to form 2,4,6-tribromophenol. So what would that look like? So that's carbon number 1. So 2, 3, 4, 5, 6. Br there, Br there, Br there. Okay, done it again. So we're going to get 3 moles of HBr, and so we need 3 moles of Br2 to balance that equation. So observations, often asked what are the observations with this reaction. So the bromine's reacted, so it's decolorized. And I've already mentioned it, white precipitate. Okay, so that's that one. And the final one is with nitric acid. So phenol reacts with dilute nitric acid. Notice that's in bold. So we'll be thinking about the benzene equivalent reaction. Phenol reacts with dilute nitric acid at room temperature to form a mixture of 2-nitrophenol and 4-nitrophenol. So what you could do, so I normally draw the reaction like this. So we've got HNO3. So let's say we'll form the 2-nitrophenol, we'll put that up here. So nitro's gone on 2, and obviously you'd make a water molecule, or you could get your 4. I'm going to run out of space here, aren't I? Sorry about that, I'll just move that up there. Hopefully that's enough room. Sorry, that's really small, and H2O. Okay, and then there's just a little reminder there. Remember that when benzene reacts with nitric acid, the acid needs to be concentrated. We needed a concentrated sulfuric acid catalyst, and we needed a temperature of around about 50, maximum 55 degrees C. So it's fairly obvious, hopefully now, that phenol is a lot more reactive than benzene. Okay, so the nitric acid reaction is a lot milder conditions, and the bromine reaction is a lot milder as well. Yep, that's right, the OH group, it's all about the directing effects, yeah. Do we need to memorize all the benzene derivatives? You need to know everything that's in this notes pack. You need to know. If you're doing, I'm not sure if you're doing OCR. I'm assuming you're called Richard. Top of the page for a second. There. So everything in this notes pack, Richard. Sorry, I didn't finish off talking to you there. You would need to know for OCR. Okay, I only really include what's absolutely essential in the notes. I sort of tease out the extra stuff that's the sort of maybe people might be a bit more interested in with other things, but these notes are basically everything you need for the exam for OCR. Right, I'm moving back here. Hopefully that's enough. Yeah, good, thank you, you're welcome. Right, so the last little bit we need to do now is the reactivities of benzene and phenol, and the directing effects that Jack has alluded to already. Right, okay. So I'm just conscious of the time, it's 7 minutes to 8. So comparing the reactivities of benzene and phenol both react with halogens such as bromine and nitric acid, but they do so in different ways and with different reactivities. So basically this table here is just a way of summarizing all the reactions. It's just another chance to write it all down, basically, which I like my students to do a lot. So the more you get this written down, the more likely you are to remember it. That's my theory anyway, and it seems to work. Benzene and nitric acid now. That needs to be concentrated. Need a concentrated sulfuric acid catalyst. Need a temperature of 50 degrees C. And that gets you the monosubstitution and a water molecule. So there are your benzene reactions. Phenol and bromine, you get 3 moles of bromine react. There's no catalyst needed, and you get the 2,4,6 tribromophenol product. It's quite hard to write this with this pencil, so small. Okay, and phenol and nitric acid. Oops, I've forgotten the OH group there, sorry about that. Just noticed that. Dilute. No catalyst needed. This will happen at room temperature and pressure, so I'll just put RTP there. And we get, I'll just go for the 2. And just put a little note there, or the 4-nitrophenol. Okay, so that's a nice summary of all the reactions that help us determine the different reactivities. No, not for OCR anyway, no mechanisms needed for phenol. Okay, so if you think about it, the only difference between benzene and phenol is this OH group, so it's got to have everything to do with that, and it does. So the reason for the difference in the reactivity is due to the presence of a lone pair of electrons in the oxygen p orbital of the hydroxyl group. Okay, So I'm going to attempt to draw a sort of flattened version of phenol. Okay, so there's my benzene ring, and there's the bond to the O, and we'll just put that hydro, because it is technically non-linear, so we'll put that hydrogen on a slight angle there. And you've got two lone pairs on this oxygen. We're only going to worry about one of them. So in a p orbital, you've got a lone pair of electrons. Okay? So what you've got here are 6 electrons in this pi electron cloud, and we've got 2 electrons in that p orbital. Okay? And what happens is we get these sort of merge with each other, these regions of space, this pi electron cloud and this p orbital kind of merge together, okay, sort of hybridize if you like, okay, and then they create, so if I just draw the flattened hexagon again, put the OH on, so you kind of get this new region of space here, whereby I'll do it in red. So there's the original pi electron cloud, okay, or the beginnings of it, and it kind of does this, if that makes sense. Hopefully it does. Okay, and obviously you've got that on the bottom as well, because you've got the, I didn't say that, did I? So this pi electron cloud, you've got a region of space above the plane of the hexagon and below the plane of the hexagon. It might look better if I draw sort of one underneath as well. I was terrible at art, by the way, so you can tell. And the regions of space both overlap, yeah? So that overlaps with that, that overlaps with that. I'm sure I do a much better job of this on my actual phenols video. Okay, let's see, just do that. Okay, so we get that. So what's happened is we've increased the number of electrons in the delocalized ring of pi electrons. It's now 8. So we've got 8 electrons in, and I just put DROPE. So that's how you can draw it as a sort of diagram, which is perfectly fine. So what we're going to say, and we'll put it into words because sometimes, you know, it's nice to sort of write as well as just draw the diagram. So what we would say is lone pair of electrons on the oxygen atom of the OH becomes delocalized. Remember, that means it's shared between more than 2 atoms into the delocalized ring of pi electrons. This raises the electron density of the pi electrons. We've gone up to 8. And because of that, it's more able to polarize or attract electrophiles. Something like that would be absolutely fine. Yeah, I'm going to explain the substitute, why it goes to 2 and 4 in a second. Okay, James, but yeah, that's why it directs. But I'll show you why on the next, I think it's on the next page actually. Yeah, it is. And then we're finished, which is great news. So hopefully that was okay. I'll just quickly run through that. So we've got in phenol, you've got your 6 pi electrons, Remember, there's a region of space above and below the sigma framework of the carbons, yeah? And you've also got a pair of electrons in a lone pair in a p orbital on the oxygen. So rather than being separate, they kind of delocalize into each other and become this region of space here, this red region of space. And you can see that that's now containing 8 electrons. So obviously 8's more than 6, therefore it's got a higher electron density. So it can polarize things, whereas benzene with only the 6 can't. Okay? Right, directing groups. So, what are we saying here? Directing groups in an unsubstituted benzene ring, so in other words, benzene itself, so in other words, that, all of the carbon atoms have the same electron density around them. So there's no difference between that carbon, that one, that one, that one, that one, and that one. They're all what we call equivalent, okay? If any of you have done any NMR, nuclear magnetic resonance stuff, you'll know what we mean by equivalent. Okay, so all the carbons have got the same electron density in a benzene ring. Okay, so when benzene undergoes monosubstitution, the substituent attaches to any carbon on the ring because they're all the same. Okay, so there's no difference between something attaching there, to there, to there, and so on. Yep. Right. In a substituted benzene ring, e.g. phenol, nitrobenzene, or phenylamine, these are the ones that we need to focus on. So I'll just, above there, I will show you, or remind you what they are. So phenol is that. Nitrobenzene is that. And phenylamine is that. Okay? Just zoom in a little bit there so you can see them a bit more clearly. Okay? So in a substituted benzene, the presence of the substituent group changes the electron density of the carbons in the ring. So the presence of that affects the electron densities of the carbons. Okay? Presence of that affects the electron densities, presence of that affects these electron densities. So hopefully that makes sense. So there are two types of groups that we need to deal with. The first type we'll look at are electron donating groups, or we can call them activating groups. Okay, so the OH and the NH2 groups are both examples of electron donating groups. Okay, and you saw that, hopefully that made sense. There's phenol, it was donating. See that? It was donating electrons into the pi system, wasn't it? So these electrons ended up becoming part of that. So it's donating electrons. You see why? Hopefully that's why it's classed as that. Okay, so let's just show this. I'm going to draw two diagrams. So I'm just going to draw a double dot there for the lone pair. So this pair of electrons basically falls into the ring, delocalizes into here. Okay, and what it does is it creates hotspots around the ring, and it creates a hotspot here at position 2 and here at position 4. Okay, now obviously I'm going to put that in as well because they're technically both position 2, aren't they? And that's position 4. So what you saw in when the bromine reaction took place with phenol, you got substitution occurring here, here, and because we got tri-substitution, we had to put something there as well, and that's why it went there, because you've got these hot spots of electron density here. Okay, so obviously that became position 6, because we can't have two 2s, can you? And you saw as well when nitration took place, again with phenol, you could make 2-nitrophenol on that side, or you could make 4-nitrophenol. Okay, so the OH group directs substituents to positions 2 and 4. Now let's just look at phenylamine. So phenylamine is this. Well, hopefully you know that nitrogen has a lone pair on it. So I'll just put it here. Okay, there's a lone pair on the nitrogen. Just remember your sort of ammonia chemistry from first year, NH3, lone pair on the nitrogen. Okay, and so that's going to do exactly the same thing. Okay, so we get these hot spots here and here. Okay, so we'll just summarize that with electron density is increased at positions 2 and 4. Now, who was it that said it? Was it James or was it Jake? I can't remember. Or Jackie. Sorry, Jack. Sorry, got your name wrong there. Now, you might find this interesting. This position, there's another system for the 2 and the 4. You've got the position 2 is called ortho. It's called the ortho position. Position 4 is called the para position. Okay, so if you think about paracetamol, it's called paracetamol because you've basically got 2 substituent groups on your paracetamol. Let me just, hang on, I will come back, I promise. Hi, nearly finished. Right, so let's just look at this first one here, okay? So you can see hopefully on paracetamol we've got the groups directly opposite each other on the ring. So you've got position 1 and position 2, position 4, sorry. So that's what we call para. Okay? Hopefully that was worth doing. Okay. If you're interested, this position here, I'll tell you in a second because you'll see it in a second. So OH groups and NH2 groups are ortho and para directing. Okay, 2,4 directors. The other type of group that we need to know about are called electron withdrawing groups or deactivating groups. So the NO2 group is the only example that you need to know about sort of from memory. That's classed as a deactivating group or a withdrawing group. So let's just draw the diagram in the middle here. So what that does is it pulls the electron density out of the ring. Probably that arrow should sort of... Okay, so the arrow is showing that the electron density is being pulled out of the ring. So that's why they're classed as withdrawing groups. And what they do is they pull electron density away from 2 and 4. So that leaves sort of hot spots, if you like, here or here. So they're both, that's position 3, isn't it? Okay, which is also known as the meta position. Okay, so they're classed as meta directors, if you're interested in that. Okay, so we're just going to say decreased electron density at positions 2 and 4, therefore higher electron density at position 3. Okay. So they're the only, for OCR anyway, I'm not sure about other exam boards, but the only directing groups that you need to know from memory: the nitro group, NO2 group, the NH2 group, and the OH group. They're the three you must commit to memory, okay? If any other directing groups feature in questions, and they do sometimes put them in, they will always give you a table to refer to, okay? So like I've said there for my students in the notes, you may be asked to deal with other substituent groups in an exam. If so, you will be given a table like this. But you are expected, see that thing in bold, you are expected to remember that OH and NH2 are 2 for directors and NO2 is 3 directing. And there's your table. So you can see in the 2, 4, and you've got the ortho and para in the table there, look. So there's the one that you need to know there, and you need to know about that one there. You're welcome, James, and that's it. We're finished.